Okay, let's get started. For the previous 2 weeks, we talked about wireless channels, right? It was pretty quick and brief review, but I want you to look at details of a wireless communication channel, and also especially we're going to review some of those things. But the small scale fading is very important, especially the concept like a fading, flat fading, or frequency selective fading. Okay, those kind of terms you'll see it all the time from the research papers or any other system, wireless system. You will see those things. So please keep in mind that that's pretty important. So let's briefly recap what we learned last week. Last week we talked about small scale fading, right? And small scale fading occurs because of this scattering around receiver. So for example, the leaves on the tree and some of the moving objects around you, there will be some small reflections and scattering around you. So those things will contribute to make a small scale fading, or sometimes called the fast fading, because when you look at this picture, that there's a path loss here, right? And you can see these two pictures together, right? This is angle theta, and again here it's theta. So theta equal to 0 means that you are here. That means you are here. Theta is the 5/2. It's somewhere here. If there's only path loss, then since we are drawing a circle with the same radius, in other words, same distance from the base station, you should receive the same power. But that is actually not the case. Because of the shadowing, remember the shadowing was a mid-scale fading? So medium scale fading, called the shadowing, we have some up and down, some of the fluctuation over time and over angle. Okay, so this is just one snapshot. In other words, one instantaneous snapshot of the same received power surface. Okay, so this surface, or the users on this red shape will probably receive the same power. Okay, this is the same. In other words, equi-receive power region. So the guys here probably receive a little bit higher, a little bit lower power, and guys here or here probably receive the higher power than average. Okay, so that's a shadowing, but it's a medium scale. On top of that, we have a small scale fading. So you put all together, that's this green curve. Okay. So if you average out the small scale fading, then you will see the red one. Okay. Look at this one. The average out the green one, average out the small scale fading, then you'll see this red one. And if you average out even the shadowing, then eventually you'll get path loss. So path loss is kind of averaging of all of those things. Let's say you are here, right, in the receiver. You average for say hour. Okay, you average your receive power for an hour. Okay, then you probably see the path loss like this, right? You'll probably get some power which corresponds to the path loss. Okay, so eventually, if you average out all of those things, then this fluctuation will probably go away because you do averaging, right? So you eventually get the path loss. But if you think about instantaneous receive power, not average, but instantaneous, this is actually what you receive, okay? Up and down. When we talk about small scale fading, there are two different aspects, and those two are very important to remember. So one is a time dispersion, and the other is a frequency dispersion. Basically, time dispersion basically means that, as you see in this picture, again, we have some reflections and scattering. Those things will be delivered to the receiver with a certain delay. So now, in order to compare, here we have a line of sight path. This line of sight path is a direct path, probably shortest path, right? This shortest path will probably will be delivered to the receiver right here. Okay. Of course, there is a certain delay a certain propagation delay, right? When you transmit signal at time t equals 0, after a certain propagation delay, d, let's say, then you'll receive, okay? But that's the first copy, okay? First, because the line of sight has the shortest path, that is the first copy you will receive. But not only that, there's some other path. That's why we call that as a multipath. We have a multiple path, right? And these other path has a longer traveling distance, right? This is shortest path. This one has a little bit longer traveling distance, even longer traveling distance. So because of this longer traveling distance, this electromagnetic wave arrives receiver with a little bit more delay, right? So this one comes this delay, maybe this one comes even larger delay. So all these different delays is because of this different multipath, and each one is traveling different distance. So we see this kind of channel impulse response, right? So that's a channel impulse response. In signal system, you probably learned the concept of impulse response, right? So this is a block. In this case, in our case, this block is a channel. Okay, this is channel. We just think this whole channel as a black box, right? And here, the input is the transmit signal. The output would be the receive signal, okay? And we want to understand the impulse response of this block. How do you know? Okay? How do you know is that we have to measure it. But in order to measure it, based on the definition of impulse response, the transmitter has to transmit the impulse, and you should receive something, right? That would be the channel impulse response or impulse response of this block. So if you do that, then although you transmit impulse, you probably receive multiple impulses because of this multipath, right? So that is a channel impulse response, and understanding this one is very important, especially probably sometimes it matters how many significant paths we have. That's one thing, one of the things that we have to know. Another important thing is how much these delays or multipaths are spread over time. That's another important factor. So that's called the delay spread. Although you have two paths, let's say you have one here, another one here, there are only two multipaths. Sometimes the delay between these two paths would be very large, right? That's also bad. Large delay spread is a little bit bad for us. Also, many multiple paths, again, it's not good, right? So, but we need to understand this time dispersion by looking at this power delay profile. This is called the power delay profile. So that's required to design our system. Another important thing is frequency dispersion. As you remember, this frequency dispersion happens because of the Doppler frequency, right? Okay, so because of the Doppler frequency, in time-wise, you have a fluctuation. If the Doppler frequency is, say, 0, of course, there's no such things, but suppose that it's a 0, that means that you probably have no fluctuation. Okay, here's what we can see, right? Let's say in frequency domain, let's assume that frequency domain you have an impulse, right? In time domain you have a flat, right? So now let's say that you have no Doppler frequency. In that case, you have your own signal. It's not an impulse, so you have your own bandwidth, right? So let's say this is a frequency. This is your bandwidth, your signal. Now let's say Doppler frequency is 0. So this is what you transmit. This is what you receive. But now let's say there is a Doppler. In that case, what that basically means is that if there's a Doppler frequency, then transmitter transmits this impulse, say, in the frequency domain, or this is a sinusoidal tone, that will be spreaded, right? This is, let's say, FC, but you will receive some other frequencies. And the maximum Doppler will be FM. So sometimes you receive FC plus FM, or some other times you receive some other frequency. So the frequency is now this is frequency dispersion now, right? The frequency is now changed, but it's not changed into just one. This will be spread over the frequency domain. Okay? This frequency spread will contribute a time domain fluctuation. Same thing, right? Let's say in the that's actually the same thing. Here also, right? In time domain, you have a delay and multiple path. Because of this multiple path, in frequency domain, you have a fluctuation. If you have only one impulse, which is very ideal system, right? Because you have impulse at the transmitter, you receive just impulse. That means everything is perfect. In that case, the frequency response of this block would be flat because you receive the impulse, right? Just the frequency domain impulse means that time domain flat. But that's not the case. You see that there's a multipath. So because of this multipath, if you look at this frequency domain response of this block, there will be a fluctuation. Same way, if there's some of the spread in the frequency domain, that will contribute the time domain fluctuation. Okay? So that's a frequency dispersion. So if you have more dispersion in the frequency domain, you have faster fluctuation. If you have a small spread in the frequency domain, you will see a little bit slow fading. Okay, so this is low Doppler frequency case, high Doppler. And as you know, the Doppler frequency is because of the mobility. Sometimes the mobility of the transmitter or mobility of the receiver or both, or even mobility of some other objects in between. Okay. So as we already mentioned, the delay spread is one of the very important factor. Okay, very important factor. As you see, here is a power delay profile. Okay, this power delay profile is actually from measurements. That's the only way that we can get this one, right? Because we are talking about the channel, wireless channel. There's no way that we can, no other way that we can measure the power delay profile. But it can be only measured. So how to measure it is that we transmit some signal. There are several ways to do it. If you took my wireless communication course in the last semester, then we talked about 3 different ways how to measure the channel. But whatever way you use, anyway, the power delay profile has to be measured. So you transmit some signal and you receive some of the signal, and by looking at the received signal, you can measure it. So let's say this is a power delay profile of a certain environment. That means that you have a highest peak that possibly is the line of sight path, and you have a multiple path, right? And since this is from measurements, you probably see this kind of up and down a little bit and further. And at some point, what we have to do is we have to decide where is the noise level. So as you see here, it says a normalized received power. That basically means that the actual power here is something like minus 90 dBm or something. But we don't care about the actual power level. What we care is that we want to make the first path or the largest path, or strongest path as a reference. So we make this one as 1. So in dB scale, it's going to be 0 dB. Okay. So we use this one as the reference, okay, and change all of the scale based on that. Okay. So the first one, which is the strongest one, in fact, the strongest one, we make it 0 dB, and all the others will be like minus 10, minus 20 dB, something like that. Okay. So that's what they mean as a normalized. And now you need to decide where is the noise level. So in this case, this line, okay, this line is noise level. So once we decide this is the noise level, then we're going to ignore all the samples below it because we consider that as a noise. Then think about only the peak that is above this noise level. Then now we see that still there are significant number of paths, and even here, right? But there's pretty much nothing here. So from that, we can simplify this picture and make a power delay profile. If you want, then you can make this as one impulse, another impulse, another impulse. You can make maybe, in this case, maybe tens of impulses, right? Or depending on your system, you can actually even simplify further, okay? But that's up to you. But how to make actual power delay profile like this one, this is eventually what we want. But in order to make this kind of thing, you need to do measurement. But in this case, as I said, there are many paths. So how to convert this one to that kind of picture is up to you. If we have time, then we can talk about this sometime later. But there's such a technique how to convert from this one to that. Okay. But from this picture, we measured this one, and from this one, we calculate the delay spread. Okay? And remember that we talked about 3 different parameters. First one is a maximum delay spread, which means that we basically measure the distance, measure the delay between the first one and the last one. Okay? This would be the maximum delay. Whereas there's a mean excess delay, meaning that you take average of these things. Average does not necessarily mean that it's the middle, okay? Because here you have a high peak, okay? You have higher weight, whereas this one is small, so it'll be a little weight. So when you take the just average, like this one, right, mean, then it's not going to be somewhere in middle. It's going to be somewhere here, right? Because you have a higher weight here. It's like a weighted average somehow, right? So that's what it is. You see that this is a delta. This is tau, means the delay for each of them, each path. But this one is kind of weight, because this one basically means the power of each path, right? So by multiplying the power of each path with its delay, you are taking weighted average. So if you take the mean excess delay, that's going to be somewhere here. More popular thing is a delay spread, or sometimes called RMS delay spread, which can be calculated this way. Okay, this basically means that you look at this one. This is a second moment, and this is the average, which is this one, average square. Okay, so think about the statistics or probability that you learned before. This one is same as a variance. Okay, variance. Okay. And this delay spread, RMS delay spread, is the most popular parameter that everyone uses. Okay? So simply speaking, this is the reason that why we want to measure this power delay profile, one of the most important parameter. And why this is important, probably we have a chance to talk about it later. But simply speaking, right? We need to understand how much it is spread. Here, now we're going to talk about a flat fading and frequency selective fading. Here, the tau, the sigma tau, this is the delay spread. Okay. In our case, we're going to use the RMS delay spread. But think about it. If you have an RMS delay spread, and let's say large RMS delay spread, that basically means that you have a low or small coherence bandwidth. Okay? Why is that? Again, same way. When you have a large time dispersion in the time domain, that means in frequency domain you have a small flat region. Okay? So that's the definition of coherence bandwidth. See here, coherence bandwidth is the range of frequencies over which the channel can be considered flat. Okay, so this is the spelling error. Okay, so that's a coherence time, coherence bandwidth. Coherence bandwidth is inversely proportional to the delay spread. Okay, that's what is important in this slide. Similarly, if you think about time coherence, okay, coherence time, that basically means that over time domain, how long your signal is flat, is considered flat. So that means that this coherence time is inversely proportional to the Doppler frequency. As I said earlier, if the Doppler frequency is 0, let's say this is 0, then coherence time is infinite. Means that you have flat. Over time, coherence time is flat. Okay? But if you have a certain Doppler frequency, then you have a certain coherence time. Let's say your Doppler frequency is very large because of high mobility. Then you have much faster fluctuation. Okay? So the time duration where the channel can be considered as a flat or signal is flat, that's pretty short. Okay? So that's inversely proportional. So simply speaking, when you have high mobility, that means high Doppler, that means channel is fluctuating much faster. Okay? Therefore, coherence time is very small. Okay, so we talked about the fast fading and slow fading depending on the Doppler spread or Doppler frequency. Now it's time to talk about flat fading and frequency selective fading, right? I guess if you remember the slide, the previous lecture, we talked about flat fading and frequency selective fading, right? Since this is a summary, I skipped those things. But let's briefly review definition about flat fading and frequency selective fading. What was the flat fading? Flat fading basically means that if you look at the frequency domain, your signal is almost flat. That means flat fading. Okay? Frequency selective fading basically means that over this frequency region, your frequency response has a lot of fluctuation. But now that depends on your sampling frequency. Okay? So as you see here, the delay spread, if the delay spread is lower than sampling period, then it's flat fading. Remember that delay spread is this much. That means you send the impulse, that will be spread only this much, but your symbol is this big. That's what this means, right? Symbol period is pretty large, so your symbol is big. So even though you have some delay spread, like this small, that doesn't really matter because anyway my symbol is big, so I can take the sampling in between, I can recover without any problem, right? So delay spread doesn't matter, okay? That's the case of flat fading. That's the time domain, but if you look at the frequency domain, the same thing. That basically means that when you have this kind of delay spread, let's say this is channel impulse response, when you have this much of delay spread in time domain or in delay, then if you take this one and go to the frequency domain, that basically means that you have frequency response of this much. This is a frequency response of the channel. Okay, we are talking about only channel. This one is a channel impulse response. This is channel frequency response. Okay, given this channel frequency response, when you design a system, let's say your system has only this much of bandwidth. This is your system. Okay, you have only this much bandwidth. So it's kind of narrow band system, right? Narrow band. So when you design a narrow band system, your bandwidth is pretty narrow, and within this bandwidth, your bandwidth, the channel does not fluctuate inside, right? It's pretty much flat. So that basically means a flat fading. This is a case of flat fading, right? So compared to the channel frequency response, right? Your signal bandwidth is pretty narrow, such that within your bandwidth, the channel is considered almost flat, right? So that's a flat fading. Okay, that basically means the same as this one. This is the time domain concept. This is frequency domain. Basically the same. In the frequency selective fading, that's the opposite. So we have a delay spread of this much. So you send the impulse that is a spread in time domain this much. That's a delay spread of this much. But your symbol is actually pretty tiny. So that basically means that you will see a lot of inter-symbol interferences, right? Inter-symbol interference, a lot of them. If you see those things in the frequency domain, now it's the same. Let's say we consider the same channel impulse response, okay? Then we again have the same channel frequency response. Now what I want to do is that I want to design a wideband system, let's say. Now I like to have a wideband system. So in my system, since this is a wideband, I'm going to take this much of band. This is my bandwidth. In that case, within my bandwidth, I have a lot of fluctuation, channel fluctuation. So this is called the frequency selective fading, because for each frequency, you have a very different channel. Okay? So depending on the frequency selection, you have a different fading. So that means frequency selective fading, right? So this is a frequency view. This is a time view. Basically the same thing. Okay? It's the same thing. So you need to understand all these things in very detail. That's very important. Okay? This understanding flat fading, frequency selective fading in time domain wise and frequency domain, it's very important, right? We also talked about the Rayleigh distribution, because you will see the Rayleigh in everywhere when you look at the papers. So mathematically, Rayleigh distribution looks like this. This is a PDF. This is a CDF. Okay? And Rayleigh distribution has only one parameter, sigma. So depending on the actual sigma value, you have a different PDF or CDF. And the reason that we want to understand the Rayleigh is because that this Rayleigh actually matches exactly the physical phenomena. Let's say that how we get the Rayleigh. We can start from an environment where we have a receiver, we have a transmitter somewhere, but we don't care where it is. And suppose that there's no line of sight. Okay? There's no line of sight. I'm here. I'm basically receiving a signal from base station, but I don't know where is my base station. And especially, I'm here, so the line of sight is completely blocking. So that's the case. Okay, there's no line of sight. In that case, your transmitted signal from somewhere will eventually arrive at the receiver, but after just some scattering around the objects around me, right, or some of the moving objects. So mathematically, we can model this one as receiver is getting millions of different waves. Each wave, we can write it as a complex value like this. Okay? And eventually, my received signal, which is xt, okay, xt equal to x1, t, x2, t, dot, dot, dot. So I'm adding all these electromagnetic waves. And now we can apply the central limit theorem that we know that when you add all these different random variables, then we don't care about the statistics of each random variable. Once you add all these things, a lot of things, then the result, the x, basically follows a Gaussian random variable. That's the central limit theorem. So we know that this xt, based on this central limit theorem, xt follows a Gaussian random variable. Okay? And now what you're interested in is to find out the amplitude. Okay? Amplitude of the received signal. And especially this xt is the complex value. So xt equal to a plus jb. Let's say let's say this we can say that this xt, which is a received signal, is a complex, and this xt basically follows a Gaussian. This is Gaussian. This is normal distribution with the zero mean and certain variance, okay, certain power. Now what we are interested in is a amplitude of the received signal, okay? This is the received signal. We want to find out the amplitude. And as you know, the amplitude of the complex value would be this one, right? And that's my amplitude. Let's call that as A. A is my amplitude. And as you see, this is a Gaussian, this is Gaussian, another Gaussian, and the square of the two different Gaussian and sum, and you put the root square of that, that's going to be a Rayleigh distribution, okay? So that's how we get this Rayleigh distribution, and that's why this one has a lot of meaning, okay, in wireless communications. Similarly, sometimes you see a Ricean distribution, and Ricean distribution has this kind of PDF and CDF. And the environment of a Ricean distribution is where you have a line of sight. Now you have a transmitter. I can see my transmitter. Okay? I have a line of sight. You have a line of sight, and there are also a lot of waves coming in from all different angles. In that case, mathematically, again, you are adding all these different waves from all these different directions, but one of them, especially here in this case, this one, line of sight path, is not zero mean Gaussian. Okay? So eventually, when you add these all together, one of them, let's say x1t, this is not zero mean Gaussian, this is non-zero Gaussian. So adding all these things eventually result in this x of t, which is the addition of all these different random variables, would be non-zero Gaussian. So x of t is a non-zero Gaussian. So the only difference here is that this one now is not zero mean, but this one has a certain mean. And this m mean would be the strength of the line of sight. If you have a very strong line of sight, that means you have a high m. Okay? In that case, you again do the same thing because we are interested in amplitude. Now this xr and xi, this is non-zero mean Gaussian. Then you calculate the amplitude. That's going to be a Ricean. Okay? So remember that what is the environment of Rayleigh and what is the condition of Ricean distribution. We also talked about some simulation of Rayleigh channel, and this is called the Jake's model, one of the popular models. And this model basically try to do a summation of all the sinusoids. We have a sine waves, cosine waves. You just generate in your simulator, right? And then add it together to make a fading channel. Another way to simulate a Rayleigh fading channel is Clark's and Gann's model. So as you see here, again, here also you generate the noise, the Gaussian noise samples, right? And you generate the Gaussian noise samples and you modulate it and sum it, okay? Why do we do that is this one. This is the reason. Mathematically, we are doing this, right? We are making a Gaussian random variable in the real and imaginary, and then we take the amplitude. Then we know that the result will be Rayleigh. That's exactly what's happening here. Okay? Okay, and especially here in the Clark's and Gann's model, you want to apply the Doppler filter. The reason that we want to apply the Doppler filter is because that we are basically simulating the channel, right? In actual channel, you have a Doppler frequency. Without Doppler frequency, what happens is you have a flat over time. So you won't see any fading over time. So in order to see the fading, you need to have Doppler filter. Okay? Doppler filter will Doppler filter looks like this one, and Doppler filter will take the Doppler frequency. So you have to specify your own Doppler frequency, and make this kind of Doppler filter, and based on that, we basically make a time domain fluctuation of the channel. So this is actually simulated fading channels. This is the case of fading the Doppler frequency 50. This is the case of Doppler frequency 200. So you see that this is this is faster fading, slow fading, okay, in time domain. Okay, today and the next week, for the 2 weeks, we're going to briefly review multiple antenna system. Some of you probably took my MIMO course last year, right? But for those of you who took the course, this is going to be a review, I guess. But for some other students who are not familiar with the MIMO, this is probably a chance, okay, to learn something about it. But we have only 2 weeks, so I'm going to briefly review. So whenever you have questions, then ask me. Then we can go into details, okay? So in order to talk about MIMO, or MIMO is called multiple input, multiple output, okay? In other words, multiple antennas. Before we talk about multiple antenna systems, we have to start from single antenna system, because everyone knows the single antenna system, okay? So single input, single output, that's SISO. The reason that we called single input, single output, or multiple input, multiple output, for multiple, we are talking about multiple antenna system, right? But no one here in this context, you don't see any term antenna. We see only input output. The reason was that this terminology came from a control theory long back, like 30 years, maybe 40 years ago, okay? At that time, people are only talking about the block diagram, and you have a block diagram, and you have a maybe single input, single output, multiple output, okay? And that kind of concept still exists in wireless communication. So think about this way. This wireless channel, okay? The channel is now a block diagram, and that's our focus, okay? We have this block diagram, and that's our focus. And from the channel perspective, this transmitted antenna is the input. Receiver antenna would be output, okay, from the channel perspective. That's why we say single antenna system is called the single input, single output. And MIMO, multiple input, multiple output, you have a multiple antennas, in other words, multiple input to the channel. Multiple antennas at the receiver means the multiple output, okay? So that's why we call this MIMO SISO, okay, from the channel perspective. Okay, the single antenna system, we can think about the performance limiting factor, okay? In the transmitter and receiver, especially the transmitter, you always have a resource budget, especially the power budget, okay? You have a certain limited power budget. Why we are talking about this is because that if there's no such restriction, let's say you can transmit whatever power you want. In that case, the easiest way to increase the performance is to boost up your power, okay? If there's no restriction, you can boost up power. Then that basically means that you can increase the performance, okay? But that's not the case always, right? There's a certain restriction because of many, maybe based on the standard, based on the regulation of the government. But whatever it is, there is a restriction always. Especially the transmitter, you have a certain power restriction, okay? You cannot transmit the power beyond some certain level. There will be always power budget. There's also bandwidth restriction, okay? You cannot increase the bandwidth like gigahertz, okay? You are given only a certain limited frequency band. So that's another restriction. So given this restriction, there's a certain limit where you cannot easily increase the threshold beyond that. Okay, so our focus is that given this restriction, we want to have a high performance system, but because of this restriction, we cannot go beyond a certain performance. That's the motivation. especially also the channel. Look at the channel here. We have some bad characteristic of the channel. We have a fading, as we just talked about, with a Rayleigh fading or Raysian or some other fading. We have a multipath, delay spread. We have a mobility, Doppler spread, and we just looked at all these things, right? So we are talking about wireless channel. But remember, this channel characteristics, multipath, mobility, fading, these things, you have to go with it. You cannot remove it, right? You cannot remove a multipath unless you change into some other environment, okay? This one, you have to go with it. So the only thing that you can do is that given that there is a such bad thing, you have to try your best in order to undo those things, okay? In order to remove those things, okay? You can try your best, but you cannot ignore these things, okay? You cannot control the channel. Channel is there, you cannot control it. Okay, so here is the restriction for us. Now, given that restriction, let's go to the basic. So what is the best way or easiest way to increase the performance? The easiest way is to use more frequency band. You are using one frequency. Easiest way to increase the performance is to use another frequency, additional frequency, right? If you use more frequency, that would be such as that's like if you think about the road, right? Road on the street. This is going to be a lane, one lane, and if you want more traffic, you can make another lane. So if you think about the wide, maybe 4 different lanes, you have more traffic. Increase the lane, okay? Lane, then you have more traffic. So if you want more traffic, this is easier way to do it. Increase the frequency band, right? In the frequency domain. Another way that we can think about is the time domain. Okay, in time domain, you basically split the time into several time slots, okay, and use this time slot differently. And this concept basically comes and try to take advantage of what we call as time diversity. What that basically means is this one. As we know, we have a time fluctuation, okay, because of this fading. So what that means is your signal undergoes a time fading. So sometimes your channel is very bad. Some other times your channel is good. So it's like fading like this, right? So if you know that for this certain frequency, at this time, if a channel goes very bad or deep fading, then maybe you can jump onto another frequency, okay? Because that another frequency may give you some good channel at that same instant time, right? So you can take advantage of those things. Another guy also do the same thing. Another guy normally use another frequency, but that frequency sometimes goes bad. So in that case, you can jump onto another frequency, okay? Which gives you better condition. You see what I'm saying? So that's kind of concept of time diversity. So anyway, these are the resources, frequency or time. These are the resources where you can use it in order to increase the performance, right? So think about our traditional wireless system. FDMA or any frequency domain and TDMA, they use the time domain. Those two basically use these resources in order to have the more users, okay, more resource, more throughput. Now, okay, our focus is this one. We don't want to increase the frequency, okay? We want to use only this frequency. Of course, it's very straightforward. If you increase the frequency, you get the better throughput, but we don't want that, okay? We want to limit our frequency and also time. Then what is another way to increase the performance? That's where the MIMO basically comes in. So here's a simple picture. As I said, the frequency, one frequency band, another frequency band, that's almost same as the lane on the road. Let's say this is a road. Okay, let's put some time axis, frequency axis on the road. Okay, I'm basically looking from the top. Okay, we have some cars, some red car, white car, and let's say these are all the traffic, or you can say these are all the different users data. Okay, so each user will use some other lane, in other words, frequency. But what I want is I want to have more traffic. Okay, or more throughput. Okay, I want to have more cars in this area. Easiest way to have more cars in this area would be you can build a more lane, but I don't want that. That basically means that I need to have a more frequency. Let's say I have no more frequency available. Okay, this is not a choice for us. Okay, this is the only frequency we can use. Now then, what else can you do? You can do it this way, right? Think about the three-dimensional space. You have a lane here. You can put another lane on top of it. Like you have a lane, you can on top of it. So now you can think about the space concept. Here's here's frequency. You have a 4-lane road here. I want to have another 4-lane road on top of it, which is independent from the first road, right? In that case, in this area, you can have more traffic. We have existing road, we have a new road on top of it in a different space, so you can have more traffic. Okay? Basically, similar concept. So when you add some more antenna, that expand a space into, that is another dimension. We expand the space dimension. You see what I'm saying? This space dimension, okay? So this concept is almost similar that we earlier used one antenna, but now we have more antenna, okay? More antenna means more dimension, maybe it's space dimension in this case. There are several ways to think about the multiple antenna system. Easier way, maybe first thing is what we call as a single input, multiple output. Again, from the channel perspective, we have one input, two output in this case, right? So single input, multiple output. It could be 2 or 3, multiple, okay? Multiple output or multiple antenna at the receiver, you have a single input or single transmit antenna. That's called a SIMO. You can do it the other way. You have multiple antennas at the transmitter. You have a single antenna at the receiver. Okay, in that case, that's a multiple input, single output, right? That's also possible. Multiple input, multiple output. This is multiple antenna at the transmitter, multiple antenna at the receiver. This is called the MIMO. You have a multiple input to the channel, multiple output from the channel, right? This is we call as a MIMO. Or someone called MIMO, okay? MIMO, MIMO, whatever you say. We can also think about different system called a multi-user system. If you think about multi-user system, then now, since this is a multi-user, we are talking about two different users. And in this case, each user has a single antenna. Okay? So this picture, MIMO, this picture, multi-user system, looks pretty different. But from the mathematical point of view, these two can be considered almost similar. The reason is that from the channel perspective, okay, let's look at from channel perspective. This one, you have a 2 input, 2 output. This one, again, you have a 2 input, 2 output. It's the same. Doesn't matter you have two antennas at the one receiver or single antenna and 2 users. Doesn't matter. From the channel perspective, you have 2 input, 2 output. The only difference, however, very big difference, comes from the processing at the receiver. The difference is that here, in MIMO case, these 2 antennas are co-located at the receiver. So one receiver have 2 antennas. So the receiver, this receiver, will take the signals from 2 different antennas, and joint processing is possible in this case, right? But in this case, now you have 2 antennas, but each antenna the antenna are separate, right? These two antenna are separated because we are talking about two different users. These two users do not talk each other, right? So they cannot do the joint processing. You see that, right? So that's a big difference. In fact, because of that, this one actually is very different. But if you look at some research papers on MIMO, some people assumes that users can cooperate, maybe using some of the backhaul communication or some background communication. Some users can cooperate. In that case, maybe you can consider this one almost similar to this one. Because if you think about the cooperation anyway, that sometimes can be considered as a joint processing. In fact, these two can be different, but the details we can talk about later. But that's some people do it, okay? Because this one is pretty difficult to solve. Sometimes you can try to change this system into like this, okay? Then a lot of things getting easier. Joint processing allows you many things. We can also think about some other system, like in this case, two antennas, the transmitter, and the two users, but in that case, each one has two antennas. So somehow, this is like 2 input, 4 output, right? 2 input, 4 output. However, maybe that's one way to look at it, 2 input, 4 output. But typically, when we look at this system, this is called a multi-user MIMO, okay? Because we have a multi-user, right? This is MIMO. Especially when you look at the multi-user MIMO, one of the things that you want to consider is the scheduling. So here's an easy way to do, right? We have 2 input, 4 output, so it's a little bit difficult to handle. So easier way to do is that we have 2 users, but let's take only 1 user at one time. Okay? At that time instant, one time instant or time slot, I'll choose this user. And the other user just keep silent. And maybe take a next time slot, you can take user 2, user 1 become silent. Okay? That's kind of user selection is user scheduling, right? So how you choose a user, and only one instant, you're gonna use only one user. So in that case, if the user 1 is selected, that's gonna be just a MIMO, 2x2 MIMO, because the other guy is silent, okay? But at another time, you switch another 2 user, depending on your condition. That condition is defined by scheduling algorithm, okay? So somehow the multi-user MIMO is not just the MIMO, it's somehow related, very closely related to the scheduling. This is another scenario of a multi-user MIMO. The next picture shows a very different setup. So in this case, right, we have 2 transmitters, and each transmitter uses 2 antennas. And here we have 1 receiver with the 2 receive antennas. In this case, right, what is actually happening is that typically transmitters are like base stations, like our base station, right? In cellular system, we have a lot of base stations. Now think about that. These are the base stations, and this one is a user. Base stations will never turn off, right? In earlier case, when you think about multi-user case, as I said, depending on your user scheduling algorithm, you can select this user, the other user, it's just keep silent, okay? It does not turn off, it's still awake, but this user keeps silent, okay? You can do that, but in this case, think about this is a base station. Base station will always transmit. So now, this environment, what is going on is there are 2 transmitters transmitting some signal. We have only 1 receiver. In that case, what happened? You will see a very strong interference, okay? Like this one, right? I'm the receiver, and these 2 guys are talking to me at the same time with a similar power that I cannot understand anything, okay? That's what's happening. 2 guys are talking same time. So you will see an interference. This is pretty much the most important environment for us nowadays. Okay? We are living in an environment where you see a lot of interferences, especially for wireless channels, wireless system. We have interferences everywhere, especially cellular system. Again, we have interferences everywhere. Okay? So this is very interesting environment for us. Now let's review some of the concepts related to MIMO. So first thing is array gain. Okay, it's energy efficiency. So what is array gain? It says that improve the signal to noise ratio or increase the coverage. So array gain that comes from the number of antennas. Let's say you have one antenna, okay, and one receive antenna, one transmit antenna, one receive antenna. Compared to that case, if you increase the number of antennas, that will provide you some gain, right? Because you have a multiple antenna, something should be better, okay? That is array gain. When you have a multiple antennas, depending on how you use it, you get the array gain. It means array, right? Array means you put something in series, okay? In cascade. That's the array. So you'll get some array gain. That typically contribute to improve the signal to noise ratio. And if you have an improved signal to noise ratio, sometimes that result in the improved coverage or increased coverage. Another thing is that you can achieve a diversity gain. Okay, we'll talk about the details of these things sometime next slide. But the diversity gain is increased, but increased diversity gain will result in a low error rate. Okay? You can reduce the error by increasing the diversity gain. When you have a multiple antennas, that actually contribute to signal to noise ratio, and also that contribute to lower error rate. So basically it's good, right? And you can also achieve some higher spectral gain. Okay? That's also called the multiplexing gain. Again, we talk about details. Next slide. So when you increase the multiplexing gain, that basically means that you can transmit more data, more throughput. So these two are different, right? This one, which called the diversity gain, the goal is to reduce the error. That's the goal. This one is that you're trying to increase your throughput. You want to transmit more data. That's this one. Okay, we'll talk about it, okay? And interference reduction, this is another thing that we can do with the multiple antennas. So these are simply speaking, these are some of the reasons why we want to use the multiple antennas, okay? These are something that we want to achieve. Some obstacles, some of the limitation of MIMO. Of course, you have multiple antennas. Sometimes you have multiple RF chains. What is an RF chain? When you have antenna, right, you should have some RF component. Okay, some RF devices, some of the mixers, and all the RF hardware. So all those things is called RF chain. Okay, so when you have multiple antennas, you are adding a bunch of hardware, not just antenna, but some other hardware also. So some of the RF chain. So that actually increase the cost, increase the hardware, increase the complexity, increase the many things, increase the cost, especially power consumption, and things like that. So that's one of the limitations. Well, even with this limitation, a lot of systems these days try to use multiple antennas, right? We know that we have some of the obstacles, but still the gain that we can achieve from multiple antennas is sometimes bigger than this one, so we don't worry about this that much. We use multiple antennas. It's pretty popular these days. And also size. Think about your cell phone. Your cell phone is pretty tiny. So we know that if we increase number of antennas in your cell phone, that probably gives you higher performance. But because of its size, simply we cannot put the more than 2 antennas. You know that every cell phone you have has 2 antennas, right? So the multiple antennas is already there. Okay, it's not new. Okay, every one of you have cell phone, and that cell phone has 2 antennas these days. And laptop also, right? You guys are using a wireless LAN, right? Laptop has 2 antennas also. Okay, some of the basic way of using multiple antenna. We'll talk about that. Here's some simple illustration. Some of you may remember this picture if you took my previous course. So this picture is just to illustrate, just for illustrative purposes. Okay, so don't confuse that this is not true, right? I'm just illustrating just to help you to understand. Okay, just for helping you understand. Okay, let's compare the SISO and SIMO or MISO. Okay, multiple antenna case and single antenna. Now, as I talked about earlier, we can think about the channel as a black box, right? From the channel perspective or the black box perspective, we have 1 input, 1 output. Now, I'm going to replace this black box, which is channel, to the water pipe. Okay, I have a water pipe. What is the water pipe for? You want to deliver water over through this water pipe, right? That's what is that for. So let's deliver some water. Okay, the same illustration. Okay, I want to deliver water. This water, in that context, water is same as data. I want to transmit data. That means in this illustration, I want to deliver water. Okay? Of course, I want to deliver more water, right? That depends on what? The size of your pipe. Okay? Your pipe is this size only, so you cannot transmit that much water. You can only transmit so much. So here is a water pipe. Now the thing is that this water pipe is not perfect. That's the problem. This water pipe has some of the cracks, some of the broken points. So there will be leak somewhere. Okay? Think about that way. Okay? Here in this case, you have some leak, right? Some small hole. So there will be some leak of water, but still the major stream goes. So you will receive something. It's not perfect, but maybe you will receive say 90% or 95% of your water. Okay, that's the condition. That's somehow similar concept as wireless channel. When you transmit data over wireless channel, because of fading, because of Doppler, because of multipath, of all this bad aspect of the channel, you will have loss. Your data will go into error, right? That error is almost same as water leak. You lost some of the information, right? So that's considered as a bit error rate, right? So how much error you have, that's same as a bit error rate. Your error, your bits, your information will be lost. Some of the errors, right? So that's like this. So if you consider a very bad channel, that means we have more leak. Okay, that's how I illustrate. Now let's consider a multiple antenna case. We have 2 different things. Let's say we have a single antenna transmitter, the same thing. We have a multiple antennas at the receiver. Okay? Or another thing is that I can put the multiple antennas at the transmitter, but all single antenna at the receiver. So this is SIMO, this is called the MISO. Okay? In that case, how I can illustrate is that if you have a multiple antennas at the one end, receiver or transmitter, at one end, if you have multiple antennas, that's almost the same as you have one pipe, same as here, right? One water pipe, but now I have a smaller hole, smaller crack, okay? That's almost same as that. And also, if you look at it carefully, this water pipe is thicker. You see that? Thick? You see that? The thick? This is a thin, but this is thick, right? But the thick base means that this water pipe is a little bit stronger and thicker. Therefore, you have a smaller leak, okay? Smaller error. You see that this is more error than this one, right? So that's what you can see. So this is still water pipe. I have one water pipe, same as before, but I have a less error. So therefore, let's say earlier I received 90%, as an example, 90% of the water. In this case, I can receive maybe 95%, okay? More reliable, less error, okay? That's the result by putting the multiple antennas at one end.
But in fact, we didn't do anything with the channel.
We do what?
We didn't do anything with the channel. I mean,
That's right.
The pipe is not changed. Only the input sources have changed.
Okay, that's a good point. That's exactly right. We didn't change anything in the channel, right? We are using same channel, same fading, same everything is still there, right? But by doing some of the processing at the receiver or by processing transmitter, we eventually get this result, okay? This effect. In fact, at this point, right, in the channel, like this one, the channel is exactly the same as this. So as you said, we are doing some of the additional processing at the receiver. We are using these two different antennas and using two different snapshot of the channel, snapshot of the received data. We are doing some post-processing and in order to reduce the error. However, in this case, right, you have a two transmit antenna. Now the channel here is a little bit different from this one. Because we have two different antennas, channel can be considered a little bit different. But anyway, we are doing some of the processing, post-processing, or you can do some pre-processing before transmission. Eventually, the effect is going to be, so again, this is illustration, okay, just to help you understand. Eventually, what we can see is that we get smaller error at the receiver, okay? That's the result by using this one. Now, let's think about a MIMO, okay? We have multiple antennas, transmitter, multiple antennas also at the receiver. In that case, this is a more generalized way, right? In that case, we have a multiple antennas at both ends. We have two choices. One choice is that we have a still single water pipe. And as we looked at before, we can make a thicker pipe. Okay, we have a thicker pipe, right? Meaning that we have a very small crack, smaller crack. Okay, this is one choice. Second choice is that instead of making one very reliable thicker pipe, instead of doing that, we can also do like virtually, we can make two independent pipes, two pipes. Okay, that's another choice you can do. By using two antennas at the transmitter, two antenna receiver, we can virtually make two independent pipes over which you can transmit the water. Okay, on one pipe here, another pipe here, I can transmit more waters, right? Because I have two pipes, I can transmit more water at the same time. So this is another way of using multiple antennas. Especially for this one, what is the goal? The goal is to reduce the error. Okay, I want to have less error. That's the focus of this way. Okay, we call that as a diversity. We'll talk about that later. Okay, some of the details. The goal of the second way is to increase the number of amount of water that you transmit. In other words, I want to transmit more data. I don't care about the error. In fact, you see the error. Error is much bigger than this, right? Each pipe is now, it's a little bit thin. But I have two pipes. So I can deliver more water. Although there's some errors, I can deliver more. So that's another intention, okay? That's the goal of the second method. We call that as a spatial multiplexing. Why we call that spatial multiplexing? Because we have two pipes spatial pipe. This is space, right? Space-wise, we have two pipes, and we are doing multiplexing. We are transmitting data over two pipes. So this is called the spatial multiplexing. Okay? So typically, when you talk about MIMO, and a lot of people say MIMO, often they refer to this one. And if you heard about MIMO system from somewhere, they think about that, okay, MIMO system equals more data, more throughput. Okay, that basically means that they choose this option. This is another option they can think about, but they prefer to use this one, most of the people. Okay. So this illustration, I hope that can help you to understand basic concept of what we are trying to do with the MIMO. Okay, you want to either deliver the water with the less error, or you want to deliver more water, more data. Okay. Now let's think about this transmit and receive has more antennas. Let's say we have 3 antennas here and 3 antennas at the receiver. Then what happened? If you choose this option, okay, then you have even thicker pipe. If you choose this option, now we can say we can make up to 3 spatial channels. I said up to 3, not always 3. Okay? Even in this case, right, you have 2 antennas that transmitter, 2 antenna receiver. I have 2 water pipes. That's not always true. This is only true when channel is very favorable to you, when channel is very good. If the channel is very bad, anyway, I want to have this one, but this may not be possible because channel is very bad. There's a certain cases like that, okay? So we'll talk about the details later, but I'm saying that I'm very optimistic view of this system, okay? If you have 3 antennas here at both ends, you can have up to 3 spatial channels. You can even transmit higher data, right? In that case. We talked about diversity and spatial multiplexing. So if you look at this picture, then this will help you better understanding. In diversity mode, let's say we transmit ABC. But since I have 2 different antennas, I want to transmit ABC, but I transmit like ABC onto first antenna, and I modify this ABC into a little bit different way. Still it's ABC, but I do the A prime, B prime, C prime. So it still contains the ABC, but I change it to a different way. Okay? The original information same, but I make it different way. Then I transmit. At the receiver, you receive all these things and then recover the ABC. So the amount of data that I transmit is just ABC. I just transmit only 3 characters. But since I use 2 antennas at the transmitter and receiver, this whole channel is going to be more reliable. In case of multiplexing, I transmit ACE on the one antenna, BDF onto another antenna. Okay, something like that. We'll talk about more detail. This is not exactly true. Okay, we'll talk about some details, but conceptually, something like this. You transmit one and transmit another into another antenna. And you receive all these things, you combine all together, receive 6 characters. Okay, that's the concept of spatial multiplexing. Remember that when you transmit some signal from first transmit antenna, right? That transmitted signal will be received by both receive antennas, right? This transmitted signal from the second transmit antenna will be received by both receive antennas, right? Okay, so that's one thing to remember, because this is channel. Okay, so now based on those concepts or illustration that we just talked about, now let's look at the model. Okay, simple communication model. So here is how we model the system. Again, going back to the basic, let's start from the single antenna case. We have a single antenna at the transmitter, single antenna receiver. How to model this is like, let's say we put X for the transmit signal. Okay, X is what we transmit. We have a channel. Let's call that channel as H. And definitely you will have a noise. Okay, noise is N. Okay, let's use a symbol N for noise. And what you receive is going to be Y. So mathematically, how you can write is that this Y, which is the received signal, is going to be X times H plus N, which is this one. So this transmitted signal will go through channel H, which is multiplication, and this additive channel, this is AWGN, right? Additive white Gaussian noise. It's additive, means that this is added to the symbol. So you add these together, that's what you receive. So that's what it is here. So this is a very basic model. Every wireless system, you start from this basic model, not just MIMO for every system. Okay, you start from this model, very basic model. Okay, so y equal to hx plus m. Now let's extend this model into MIMO case. Okay, now we have two antennas at the transmitter, two antennas at the receiver. We have x1, which is the symbol that you transmit over the first antenna. x2 is the second symbol, or the symbol that is transmitted from the second transmit antenna. You have two receive antennas. So the receive symbol from the first receive antenna is going to be y1. You receive the second symbol from the second. You receive the symbol from the second receive antenna is going to be y2. Okay, y1 and y2. So y is receive symbol, x is the receive symbol. Now the channel, which we call the capital H. Capital H is channel, but this capital H is going to be matrix. Why is it matrix? Because we have two transmit antenna, two receive antenna. So it's going to be 2 by 2 matrix. And n is a noise sample. And again, this is a matrix. And what's the size of n matrix? The size of the noise matrix should be exactly the same as the size of the receive matrix. I make a receive matrix y, which is y1 and y2, right? We have two receive antennas. You have two receive symbols. That will be a y receive matrix. And the noise is going to be always same as receive. The size will be always same as receive matrix, right? Because of noise, think about it. When you transmit, there's no noise. I just transmit my own data. I don't care about the channel. I don't care about the noise, right? Channel and noise affects the transmit signal over the channel. Transmitter does not even go to the channel. It's before going to the channel. So transmitter is completely out of scope. When you receive, right? Receiver will worry about noise because when you receive, now the noise is added just before the reception, and also the channel is impacting the transmit signal, right? So the receiver should worry about the noise. So therefore, you have a noise at the receiver, the first antenna. You also have another noise at the second receive antenna, right? So the size of noise matrix is going to be 2/1, same as receive. And let's put that as transmit matrix X as x1 and x2. So in that case, once we model this, that's going to be almost the same as the previous single antenna case. Y equal to hx plus n. The only difference is that now y, h, x, and each of them is now matrix. Okay, that's the only difference. Now we are dealing with the matrix. Exactly the same model. And if I write the matrix, then this is the one. Okay, that's the only difference. And now then, let's find out what is H11, H12, H21, H22 is. So this is a channel matrix, and we have a 2 by 2. The reason is that, as you see in this picture, we have two transmit antenna, two receive antennas. But the transmitted signal from the first antenna will go to this way, that way, right? That transmitted symbol will be received by two different antennas over two different channels. So H11 is the channel between the first receive and first transmit and first receive antennas. H21 is the channel between the first transmit antenna and second receive. When you write the number, typically the first one is the destination. Okay, second one is the source. So the first transmit antenna to the second receive antenna would be H21. Okay. Same way, the symbol that is transmitted from the second transmit antenna will be received by two receive antennas, right? Over two different channels, which is H12 and H22. Okay? Put them all together and make a matrix like this. then you will see this model. That's the basic model in MIMO. Okay, every MIMO system starts from this model. Okay, this is very basic, and that's the starting point of MIMO system.